Have you ever looked up at the night sky and wondered what's really going on inside those distant worlds? We often picture planets with a neat, tidy structure, a solid core, a liquid mantle, and a gassy atmosphere. It's the classic model we all learned in school. But what if the biggest planet in our solar neighborhood, the mighty Jupiter, decided to break all the rules? What if its heart isn't a solid, rocky ball, but something far stranger and more mysterious? Today, we diving deep into the swirling clouds of Jupiter to explore a revolutionary idea that's shaking up planetary science, the shallow or dilute core theory. This isn't just a new fact about Jupiter. It has a concept that could force us to rewrite the very story of how giant planets are born. For decades, the standard model of planet formation, known as core accretion, has been our guiding star. It tells a simple, elegant story. In the early days of a solar system, a protoplanetary disk of dust and gas swirls around a young star. Within this disk, tiny particles of rock and ice start sticking together, like cosmic dust bunnies. Over millions of years, they grow from pebbles to boulders, to planetesimals, and eventually into a massive, solid core several times the mass of Earth. Once this core reaches a critical size, its immense gravity starts pulling in the surrounding gas, creating the thick, sprawling atmosphere of a gas giant like Jupiter. In this story, the core is the first and most fundamental part of the planet's solid foundation upon which everything else is built. It's neat, it's logical, and for a long time, it's what we all believed. But science is a journey of constant discovery, and sometimes the universe has a surprise in store that challenges our most cherished theories. The big twist in our story came from a brave little spacecraft called Juno. Launched in 2011, NASA's Juno mission was designed to do what no mission had done before: get up close and personal with Jupiter, flying just a few thousand kilometers above its chaotic cloud tops. Its primary goal was to map Jupiter's gravitational and magnetic fields with unprecedented precision. By carefully measuring the tiny wobbles in Juno's orbit as it swung by the planet, scientists could essentially create a map of how mass is distributed deep inside Jupiter. And what they found was, well, not what they expected. According to the classic core accretion model, Jupiter should have a small, dense, and well-defined core. This solid heart would create a very specific and predictable gravitational signature. But Juno's data painted a completely different picture. Instead of a sharp, concentrated spike of gravity at the center, the measurements suggested that the heavy elements, the rock and ice that should have formed a solid core, were spread out. They were mixed and smeared across a vast region, potentially extending out to nearly half of Jupiter's radius. This wasn't a neat little nugget. It was a huge, fuzzy, or dilute core. The heart of Jupiter wasn't a solid ball, but a slushy, murky soup where heavy materials were blended with the planet's hydrogen and helium gas. This was a bombshell. The term shallow core isn't about its depth, but about the shallow, gradual increase in density towards the center, rather than a sharp, steep boundary. This discovery sent shockwaves through the planetary science community. It meant our clean, simple model of planet formation might be wrong, or at the very least, incomplete. The king of the planets had a secret, and it was time to figure it out. So, if Jupiter doesn't have the solid core we thought it did, how did it get this bizarre, fuzzy center? This is where the detective work really begins, and scientists have come up with some fascinating and dramatic theories. One of the most exciting ideas involves a cataclysmic event in the early solar system, a giant impact. Imagine this. A young, newly formed Jupiter is minding its own business when suddenly, WHAM, it gets hit by another massive object, a planetary embryo about 10 times the mass of Earth. This wouldn't be a gentle nudge. It would be a head-on collision of unimaginable power. Such an impact would be energetic enough to completely shatter Jupiter's original, primordial core. The solid rock and ice would be vaporized and violently churned into the deep, metallic hydrogen interior of the planet. Over billions of years, this scattered material would slowly mix and settle, but it would never fully reform into a neat, dense core. Instead, it would remain as a dilute, extended mixture, creating the exact fuzzy signature that Juno detected. It's a violent but compelling backstory for our giant planet. But a giant impact isn't the only suspect. Other theories suggest that the dilute core might have been a feature of Jupiter from the very beginning. Perhaps the core accretion model needs a little tweaking. One alternative idea is pebble accretion. In this scenario, instead of a few large planetesimals coming together, the core grows by rapidly sweeping up countless small, pebble-sized objects from the protoplanetary disk. This process could be so fast and energetic that the infalling pebbles don't just settle at the center. They vaporize in the hot, high-pressure atmosphere above the growing core, essentially raining down their heavy materials into the planet's gaseous envelope. This would create a fuzzy, mixed core envelope region right from the start, no giant impact needed. It's a less dramatic but equally plausible explanation that also fits the Juno data. It suggests that forming a gas giant isn't a two-step process of build a core, then grab gas, but a much more integrated and messy affair where core and atmosphere grow together. A third possibility delves into the extreme physics happening deep inside Jupiter. The pressures and temperatures at Jupiter's center are almost beyond comprehension. We're talking tens of millions of times Earth's atmospheric pressure. Under these conditions, even rock and ice don't behave as we'd expect. Some models propose that at these extreme pressures, the materials that make up the core might actually dissolve into the metallic hydrogen that surrounds them, much like sugar dissolves in hot coffee. This process, known as convective mixing or erosion, could have slowly eaten away at an initially solid core over billions of years. The powerful, churning convection currents within Jupiter's interior would act like a giant blender, dredging up material from the core and mixing it into the overlying layers. So, Jupiter might have started with a conventional core, but its own internal fury gradually wore it down, spreading its essence throughout its deep interior. Each of these theories a catastrophic impact, a messy formation, or a slow internal erosion presents a different, captivating story for Jupiter's past. The implications of this shallow core theory are enormous. They stretch far beyond just our understanding of Jupiter. If our classic model for Jupiter is wrong, it's probably wrong for Saturn, Uranus, and Neptune, too. And more importantly, it could be wrong for the thousands of giant exoplanets we've discovered orbiting other stars. For years, we've been using the core accretion model to interpret the data from these distant worlds. We estimate their masses, their radii, and then we infer their internal structure and formation history based on this model. But if the very foundation of that model, the neat, solid core, is not a universal rule, then we might have to reevaluate everything we thought we knew about these planets. How many of them were also shaped by giant impacts? How many formed through pebble accretion? How many have slowly dissolved their own cores? The fuzzy heart of Jupiter opens up a whole new realm of possibilities. It suggests that the process of building planets is far more chaotic, diverse, and fascinating than our simple models ever predicted. The universe, it seems, has a much richer imagination than we do. This journey into Jupiter's core is a perfect example of how science works. We start with a theory, we build an instrument to test it, and sometimes the data sends us back to the drawing board. The Juno mission has completely transformed our view of Jupiter, turning it from a static, layered ball into a dynamic, evolving world with a violent and mysterious past. The mystery of Jupiter's core is far from solved. Scientists are still crunching the numbers from Juno, running complex simulations to test these different formation scenarios. Future missions, both to the other gas giants in our solar system and to distant exoplanets, will be crucial in determining whether Jupiter is a strange exception or the new rule. It's a reminder that even in our own cosmic backyard, there are profound secrets waiting to be uncovered. The universe is constantly challenging us, pushing us to ask new questions and to dream up new stories to explain its wonders. So the next time you see that bright point of light in the sky, remember that you're not just looking at a planet. You're looking at a giant cosmic puzzle, a world with a fuzzy, diluted heart that holds the key to understanding how planetary systems, including our own, are born and evolve. The story of Jupiter is still being written, and we are lucky enough to be living in the era where the chapters are being revealed, one Juno flyby at a time. Thanks for joining me on this deep dive into the heart of a giant. If you enjoyed this journey into the unknown, don't forget to hit that like button, subscribe for more cosmic adventures, and ring that notification bell. Let me know in the comments which theory about Jupiter's core you find most compelling. Until next time, keep looking up,